Okay, so let's get right into it. When you think centrifugal pump, you're probably picturing horsepower, specs, and a bunch of complicated engineering charts. And you're not wrong. But what if I told you the real secret to picking the right one is less about engineering and more about matchmaking? We're going to look at this as a search for the perfect partner for your system, one that's efficient, reliable, and just works with zero drama. We've all been there, right? You turn on the shower and you get that sad, weak little trickle. Well, that feeling is exactly what happens in an industrial setting, and it's more than just annoying. It can bring a whole operation to a grinding halt. It's a classic sign of a bad relationship in the heart of your system. So to fix it, we've got to understand the players involved. And here we have our hero, the machine that's supposed to solve this whole problem, the centrifugal pump. Its job seems simple enough. Just move some fluid from point A to point B with a certain amount of oomph. But how do you know if any one pump is the right one for your job? Well, here's the cool part. The pump tells you itself. It comes with its own detailed resume, spelling out exactly what it can and, just as importantly, what it can't do. So, let's start this matchmaking process. First things first, we need to get to know our candidate. And the best way to do that is to look at its professional resume, all its performance data. This is where it lays out all its skills and qualifications, telling us exactly what it brings to the table. The very first thing on that resume is flow. You'll often see it as the letter Q. This one's pretty straightforward, right? It's all about how much liquid the pump can move. It's a question of volume. Are we moving a few gallons a minute or thousands? This is the first number you gotta know. Next up, we've got head, which is HOR. Now, if flow is about how much, head is all about how hard. It's the muscle. It's the pressure the pump can generate to push fluid uphill or to fight against all the friction in the pipes. It's actually measured in the feet or meters. It could literally lift a column of water. So yeah, just remember, flow is how much, head is how hard. Now, here's where it gets really interesting. All of these resume points, they all come together on one single elegant chart, the pump curve. This graph is basically the key to this whole matchmaking thing. It shows you the fundamental trade-off. The more flow you want, the less head or pressure the pump can give you. It also shows you the pump's sweet spot for efficiency. We call that the best efficiency point, or BEP, plus how much power it's going to guzzle, and a super important safety number called NPSHR, which keeps the pump from basically tearing itself apart. So we've seen the pump's resume. It's impressive. But even the world's best candidate is going to fail if the job itself is impossible. So now we have to look at the other side of this match, the job description. And in our story, that's the system's own unique obstacle course. I mean, think about it. The fluid doesn't just magically appear at its destination. Nope. It's got to travel through this whole network of pipes, make sharp turns at elbows, get squeezed through tiny valves. Every single one of those components pushes back. It creates friction. That is the resistance our pump's head was born to overcome. And this obstacle course really has two parts. First, there's static head. This is the fixed, non-negotiable challenge of just lifting the fluid up. Think of it like a hill you have to pump over. That hill's height never changes. Then there's friction head. This is the resistance from the fluid rubbing against, well, everything. And unlike the static hill, this resistance gets way, way worse the faster you try to go. So just like the pump has a curve that describes what it can do, the system has a curve that describes what it needs. When you plot out the total head required, that static hill plus all that increasing friction, you get the system curve. This is our job description, plain and simple. It shows us exactly how much pressure is needed for any given flow rate in our specific setup. All right, this is it. The moment of truth. We've got our candidate's resume, the pump curve, and we've got our detailed job description, the system curve. Now it's time to bring them together for the interview and see if we have a match. And this is just brilliant. When you lay those two curves on top of each other, they're going to cross in one and only one spot. That spot is the operating point. And it's not a guess, it's not an estimate, it's physics. This single point tells you with absolute certainty the exact flow and head you are going to get if you install that pump in that system. It's the real-world result of this match. But here's the thing. Just getting an operating point isn't good enough. The perfect match, the whole reason we're doing this, is to get that operating point to land directly on the pump's best efficiency point, the BEP. We want the system to ask the pump to do the exact job it was designed to do most efficiently. That's the win. Because a bad match, it's a disaster waiting to happen. If your operating point is too far to the left of the BEP, you're in low flow. The fluid just churns around inside the pump, building up incredible heat and vibration that'll just shred your seals. But if you're too far to the right, in high flow, you can trigger something called cavitation, where vapor bubbles form and violently collapse, literally eating away at the pump's impeller. Either way, you're looking at expensive failures. So, now that we know what a perfect match is supposed to look like, let's go all the way back to that frustrating weak flow we started with. What's actually happening when the match goes wrong and you're stuck with a system that just won't perform? Well, if your system isn't giving you the flow you need, it means your operating point has moved. And really, that can only happen for two reasons. Either the pump isn't living up to its resume anymore, or the system's obstacle course just got a whole lot harder. So, before you blame the original matchmaker, here's a quick checklist of the usual suspects. First, is the pump spinning the wrong way? I know it sounds basic, but trust me, it happens. Is there a clog somewhere? Have critical parts just worn out over time? Or maybe, just maybe, it's something simple in the system, like a valve that's not all the way open or a bypass line that's stealing all your flow. But what if the job description itself changes all the time? What if your system needs change from day to day? What if you could give your pump a superpower, one that lets it rewrite its own resume on the fly to make sure it's always the perfect match for the job at hand? Well, that superpower has a name, the Affinity laws. Now, don't let the name scare you. These are a set of beautifully simple and incredibly powerful rules of physics that tell us exactly how a pump's performance will change when we change its speed. Law number 1 is about flow, and it's a direct one-to-one relationship. Super easy. You slow the pump's speed by 10%, you get 10% less flow. You double the speed, you double the flow. Simple, predictable, I love it. Law number 2 covers head, or pressure, and this is where things get dramatic. Head changes with the square of the speed. What that means is a small tweak in speed has a huge impact on pressure. So if you double the speed, you don't just get double the head, you get 4 times the head. It's a massive change. And finally, the most critical one, the one that really hits your wallet, power. The energy a pump uses is proportional to the cube of its speed. This relationship is just massive. Doubling the speed means your power consumption goes up by 8 times. But more importantly, it means a small reduction in speed creates gigantic energy savings. Slowing down by just 20% can cut your energy bill almost in half. So how do we use this superpower? With something called a variable frequency drive, or a VFD. This device lets you control the pump's speed. It's like being a dynamic matchmaker. You can literally shift the entire pump curve up or down to make sure that it always intersects with the system curve right on that all-important best efficiency point, adapting in real time as your needs change. So the biggest takeaway here is that picking a pump isn't about just grabbing the biggest motor or the most horsepower. It's about finding deep compatibility. It's about understanding the pump's resume and truly respecting the system's obstacle course to create a partnership that isn't just functional, but is genuinely efficient and reliable. Which really brings us to the final question you ought to be asking yourself. Is your pump a perfect match, or is it secretly wasting a fortune?